We're going to go through the final discussion here. I have no idea what order these are in, so the first up is going to be, I guess, Rolando and Kenny's group. Just a couple of quick announcements. First off, there are a bunch of snacks in the back. If you have any desire for sugar, or I don't even know if there's any fruit back there, please help yourself. We are taking contributions of any amount of cash, cars, or whatever. Not Mike's rental car, which looks really sketchy. Yes. Secondly, for each of the groups, if you have other notes that you took in addition to these, please send them. And again, from the earlier session as well, just email them to me, and we'd love to get your input. So we're going to start off with Rolando and Kenny. Who's going to, Kenny?
Our concept is for an intelligent orbiter for planetary science. Do I change the slide? So mission concept is use of an intelligent orbiter, in this case mothership, to deploy smaller payloads for atmospheric surface science collection. Now, depending on the type of payloads, it is going to depend on where the target is and science requirements. So the ConOps would be the mothership orbiter gets to the intended operational orbit of the target. It performs target reconnaissance, mapping, data collection for X amount of time, depending on, again, what the target is and what the science and operational requirements are. And in this case, instead of a planned sequence of activities, then using, in this case, intelligent agent on the orbiter collects the data, acquires the mapping, science data, and mission objectives, and decides where and when to deploy these payloads. Some examples that we discussed as far as targets and mission scenarios: atmospheric probes, balloons, I think that was mentioned this morning for Venus. High velocity impactors to create plumes for remote sensing. This would be a good scenario for ocean worlds, for Europa, Enceladus, or Titan, basically creating your own plume, and then the orbiter basically collects the data, remote sensing of the plume, or flying through the plume in this case. Or the other example of probes, entry probes for specific instrument science measurements. I think there was a discussion this week as part of the Exploration Science Forum about not having sufficient data for Mars local climate. So probes could be seismic, weather, radiation sensors that the orbiter deploys. For example, if there's a dust storm on Mars. So in this case, the orbiter is doing its mapping, autonomous mapping, and decides when to deploy a certain number of probes or sensors to the surface to collect that data. Instead of, again, waiting for the ground or a predetermined sequence of activities. And again, based on the collected and analyzed data, in this case, we're assuming all these deployed sensors are not intelligent, so they're basically are deployed and collecting data. The orbiter, mothership, decides the subsequent activities or science collection phase of the mission. And another example would be perhaps the orbiter, if it has imaging sensors, could, depending on the collected data, again, for Mars, if there is a dust storm, perhaps the orbiter can start collecting high-resolution imagery of the target, based on the data that has been collected. Again, final part of the ConOps would be data downlink and communication with the ground as part of the nominal phase, and depending on where the mission is, it could be the communication data transfer to the ground could be a matter of hours, days. Again, you can apply this architecture to various targets and orbits. Required technologies, again, just brainstorming on the technologies that will be needed. The orbiter mothership concept, the processing capability, memory storage, power, radiation hardening, and we discussed that if we can take advantage of the future processor capabilities to address that. We call this Watson on an orbiter. So the required algorithms, certainly to train this algorithm, we can do that on the ground pre-mission based on the collected data, all the available data based on the target, where the target is. So that happens pre-mission, but then also using the state-of-the-art algorithms, machine learning, deep learning, for example, to continue the learning phase. And that would be based on the data that's been collected by the orbiter through the early mapping and reconnaissance to make subsequent decisions. Other challenges would be data storage, amount of data that we're collecting based on the deployed assets and the orbiter, the future advanced solid-state recorders or other storage means, data processing and reduction, perhaps based on analyzing the data, you could delete some of the data that is not needed and keep the more relevant, useful data. So that would be part of the algorithm processing that needs to be done, advanced. And then, of course, distributed network of sensors that could be deployed and communication of the data back to the orbiter is another technology push that needs to be done or pull. That's it. Any questions? Go ahead.
Could this concept be expanded so that instead of just one particular mission where you have no number of possible ground deployments, you're essentially, for example, have something with a fair amount of compute power that can do the kinds of things like Watson was talking about, that's able to coordinate over a whole planet. For example, we got a lot of assets on Mars right now. We put up something there that has a lot of compute power that can do the learning, that is looking at the overall surface, and can essentially interoperate with all the assets we've already got there. You get a big multiplication as compared to just doing it for one mission.
Right. The nice thing about, I think, this architecture, you can apply that to various platforms and, again, targets as well. So, yeah, you could have more of your major platform orbiter is doing all the computing and decision-making with various multiple assets, CubeSats deployed, or other smaller platforms.
So I love the idea of continuous learning. So I love the idea of continuous learning, but I can only learn if I have labels on my newly acquired data. So how am I going to get those?
I'm not the software expert here, so that's for you guys to figure out. But yeah, I mean, the continuous learning, we discussed that as well. I think Rolando, he's our software expert, if you want to jump in, is I think that's going to be a challenge because of the limited, again, storage capabilities and the required algorithm to, again, collect, ingest that data and continuing the learning process. But again, details as far as the labeling of the data and how that gets done, that's not my expertise. Probably there are others here that can answer that. Any other questions? All right, thank you.
All right, this is a mashup of groups 1, 7, and 3, and the autonomy capability that we picked was autonomous coordination. And really the key question that we asked is, what can we do in terms of missions that we cannot do with a single asset, where you absolutely need more than just one asset? Ignoring the fact that maybe with multiple assets it's fast or anything like that, but where do you really, really need it? And then the two key things that we identify were that whenever you want to capture a single event from multiple perspectives simultaneously, that's when you need multiple assets, because you cannot do that with one, at least not simultaneously, right? Because occupying maybe two different physical locations is not possible with a single system. And then the other one was capture data at multiple locations simultaneously. And we put in quotation marks kind of examples that we thought about, which are distributed phenomena that may vary in position or time. So for example, looking at the magnetic field effect on radiation or 3D mapping of the plume. And we even put together a little concept image of multiple small sets traveling through a plume and being able to do a 3D mapping that's consistent with time. And the challenges that you have that we've identified are time synchronization when you're collecting data, communicating, because you're coordinating, you usually require communication between all of the assets unless you have really, really good sensing. Power, there's more data that needs to be processed. There's the challenge of optimizing observation locations, so identifying where, if I do have multiple assets and they need to make an observation from different perspectives, what are those perspectives, right? Understanding the global phenomena from local observations, so your assets can be much smaller than the actual global phenomena, but then they need to make decisions about how to position themselves. So if they're just doing that from their local observations and the local observations of others, how do you fuse that together to, in an efficient manner, to understand what's going on and be able to, for example, track something through both position or through time? And then for that, you also need good relative localization. But the benefits are that you can now make some more robust, optimized observations of such phenomena and really large-scale in situ observations, and be consistent with time. That's it. Oh, I guess there was a question. More questions?
Any questions? We lost Terry.
Okay, was this the next group?
Yeah, and you're talking to
I'm not sorry.
All right, so our group, we're following the previous group because we had something very similar, and it did have to do with this collaborative behavior between the assets. We didn't go into the details of the sub-technologies, but we just agree with that group, and our group came to the conclusion at our table that there's a lot of advantage if we could work on some type of autonomous or agent type of fabric and environments to allow these assets to coordinate and collaborate a lot more actively. I think it's a key element and a key enabler for some future missions. If we had such an autonomous behavior, such type of capabilities, we saw one example before, but at our table we heard in heliophysics idea of early detection of flares and reaction with all the assets that may be interested in that phenomena. You could easily understand in earth science, for instance, if you see lightning strikes, that there could be fires, and if you want to have multiple assets looking at that are reacting to it, whether it's in space, aircraft, ground, things like that. But as we could have a kind of autonomous agent framework that if people want to subscribe to that, to be coordinated or to be informed so they can coordinate, we think there's a lot of value to that. Of course, we recognize that it's going to take more computing, so we think enabling technology for this is increasing the computing environment. We heard a little bit about that earlier, but if we were able to put this layer on top of these elements, I think there's a lot more to realize these intelligent sensor webs that Mike Little and Butler Hines talked about briefly. And that's all we have for that. Do you guys want to add or correct anything? So, next slide, please. I'm not sure if it came out the way we intended, but oh, I click? Oh, I click. No?
Peter, actually, I looked over your slide. That's actually perfect for our final bit, which is wrap up.
Okay, we'll do that in the end.
Okay.
Thank you.
Are there other questions for this group? Not. Ricky, could we have the next presentation then? All right, whose presentation is this? One of you is responsible.
Right, this is going to be pretty quick, but our mission is basically heterogeneous teams of autonomous robots to do lunar South Pole Aitken Basin sampling. So there's a need to determine the composition, dating, and planetary formation with information across the Aitken Basin. So this is a large structure at the South Pole of the Moon. And one robot is not going to be able to collect the samples that you need to get away from the locality bias and to be able to sample throughout this massive structure, which is hundreds of kilometers across. So the way to do that is with a team of robots. And what we would do is basically it's a heterogeneous team, so different robots have different sensors and different uses. And we would divide up the search area and communicate in order to get coverage in the minimal amount of time and to plan resources to use. For example, there might be robots that just do navigating or are throwaways that would scout hazardous terrain, and then other robots that would actually do the sample and sample return. So the benefits and consequences to this approach are, well, we decrease risk because if you have a single robot or lander trying to go there, that's a single point of mission failure. If you have multiple robots, you can take more terrain risks. You can collect multiple samples over a wide area, which avoids this locality bias. And then you also have the ability to do things that are interesting, like scout before you risk your expensive or your single instruments. It reduces your time to complete the mission if you have more robots do it. But one of the drawbacks will be, well, if we're sending more robots, things will cost more. So, and that's all I got. Thanks.
Questions for you and then that team. We have the cube. No questions? It must be getting late on a Friday after a long week. All right. Next, Ricky, if you could surprise us, please. Okay, I know which team this is.
Make sure robots can't read our output.
This is
Now
a
we
new
have to read it too.
This is a new approach to PowerPoint.
Okay. Yes. So, and I'm sorry to my team. I kind of bullied us into this, and now I'm regretting it. But we kind of took the reactive science technology as a direction. And I was earlier today inspired thinking about Apollo 17 and Schmidt with the orange soil as like that's a thing that we didn't expect there, and it stood out to a human that was there as something of interest. And they, that's the kind of science discovery that we didn't know was going to be there. And because they could react to it intelligently, we learned something that we wouldn't have otherwise. And I think about other imagery, the skylights or those swirls and the regolith that we saw earlier today. These are things that stand out as strange to us in our pattern recognition brains. And then we pick on those, and that's when we make new discoveries. So what we kind of discussed was what could we do if we had like an adaptive anomaly recognition. We kind of focused on imagery, but this could be applied to other kinds of data. And the idea is that we could give data prioritization to specific kinds of things that stand out, or we could do dynamic targeting, either posing the craft or the constellation, or turning an instrument or zooming in or getting a higher resolution scan of something. And we could actually get a kind of compression out of this. Things that are typical, or you've seen a lot of images of that, you compress those more significantly, and you send more unique examples, things that don't fit the pattern. And this could actually possibly be used for dynamic mission replanning. So if you send a probe out somewhere and the light lag makes it so you can't dynamically change it with ground control telling it, but it's, let's say New Horizons could see things in the terrain that don't fit most of the terrain, and take new frames, zoom in on particular areas as it does its flyby, we would have more specific information in the unusual areas. Does that make? Okay. Not sure I'm saying the right thing. So, we're talking about, for example, identifying discontinuities, things that stand out. And in a way, we're kind of thinking of kind of tried and true neural nets or things that are classifiers, right? And once they've classified many examples in a group A and a group B and a group C, they stop transmitting those images and now start focusing on the outliers, things that don't fit in those patterns, things that aren't closely matched to a category already. And what that would enable is we could do smaller, like CubeSats is what we talked about, and get back from it more unique instances, more interesting instances that possibly, would more likely be leading to new discoveries, right? So if we had, and I brought up the analogy of taking vacation photos. I'll go take 5 gigabytes of photos and I'll post like 5 of them online, right? I only want the interesting ones. I don't want a lot of repeats. I only want things that stand out to other humans. So challenges and opportunities. We'd like to use existing tech. I mean, it seems like these kinds of things might exist and would fit in very small, highly constrained processors and power limitations. But I don't know. I don't have a good feel for that. And then could adapt to new environments that we've never seen before, right? Going back to the New Horizons, we had a fuzzy dot for Pluto. We didn't have any categories predefined. Can it learn those on the fly? That would be a big challenge, I think. So, ready to take questions if anybody has them. Friday afternoon, I'm ready to drive back to the high desert. Okay, bye-bye.
Thank you. And the next presentation, please. Ricky. Are you going to use the black screen? Nope, too late. This one looks like Butler and team.
Okay, so we were going for the gold. We tried to go for the hardest mission we could possibly think of. So we went for interior ocean exploration, such as Europa. Science goals, search for life and characterization of the ocean environment. So we assume that we know the ice thickness, but not the subsurface topology. We assume we have a terrain map of the surface, and we assume that we're operating on nuclear power. So the mission approach is the orbiter, lander, and nuclear submarine. All 3 of them are in transit and then go into a Clipper-style racetrack trajectory to keep the orbiter out of the radiation as much as possible. A couple of passes, you're mapping the landing site. Then the lander, which is carrying the sub, detaches and then does a powered descent. The landing target is actually a fresh upwell. So the tidal forces crack the ice, and where the ice cracks apart, you get fresh upwelling that then freezes. That's probably the best target for melting through the ice because it's the thinnest ice, it's the freshest ice. It also has some side benefits that you've got a crevasse around you, so the lander landing in that is a tough landing spot. But once you're in there, the lander is shielded from radiation to a nice degree. The sub then melts its way through the ice. It leaves pucks behind for comm relay. The sub, when it breaks through the ice into the subsurface environment, there's a docking station or something. The sub initially does its survey tethered, so it's in communication, but the communication is relatively low bandwidth through the puck relay, through the tether, and then puck relay to the lander. The lander is storing forward. Whenever the orbiter in the racetrack comes within range, the lander high bandwidth data to the orbiter, which then relays it to the Earth. So you don't have continuous command, even when the sub is tethered. So the sub is doing exploration around the bore site characterizing the currents, characterizing the ocean environment. Once the confidence is high enough, and the Earth can do tweaks to the plan while it's in this mode. Once the confidence is high enough, the sub detaches and then does an aspect right under the surface where there's still terrain or surface ice features available for localization, and then establishes a sonar pinger, acoustic pinger network under the surface ice. And then you get into the sporty aspect. You have been looking for a chemical plume, and the sub follows the chemical plume to try to find a hot vent at the bottom of the ocean floor. That's the place on the Earth where there's a lot of life. It's actually life that's decoupled from solar energy, so it takes its energy from the hot vent. It's one of the prime locations for finding life in a place like Europa in an ocean. But to do this, the sub is completely detached from the surface. You have no comm relay. It's following a plume in an unknown environment. Once it gets there, it does the life assay, does the sample experimentation, and then has to find its way back within range of the dock so that it can communicate back to the Earth. So this was a stressor for autonomy in every aspect we could think of. Sarah has already left, so she assured us that this would be an easy sell for headquarters. So that the hardest drivers of the autonomy aspects are during the untethered phase, the sub is operating on full autonomy for a long period of time. That's a stretch. Fault recovery is stay alive and return and be able to return to the docking station for comm relay. So your fault recovery has to be pretty sophisticated as well to fault active recover and not passive recover. So what is needed to enable this? We were running out of time when we were doing this, but untethered localization and as one of the speakers said recently, knowing when you were lost, knowing when things are bad, right? So you need untethered localization under the surface without any navigation resources aside from the sonic pingers. Long-term operations without human input, fault response to recover actively so that you can achieve the mission and return to being in command, being in comm. And then once you're at the site, there's a chance that since you followed an arbitrary chemical plume to a location and you're not easily within range of your nav beacons, you may not ever be able to find your way back to that plume again, that hot vent again. So what you're doing in the life detection assay at the plume is a one-shot event out of contact with the Earth. You gather all the data you can, and then you depart to get back into contact with the Earth to be able to transmit the data, but knowing that you may not ever be able to find that particular hot vent again. So it's there's a lot of autonomy into this life detection aspect that you have to do out of contact with the Earth. So that was we didn't cost it out.
Take the box.
To use the magic box. So I would think this may be the type of mission which you could put together a useful terrestrial demonstration.
Yeah, that's a very good point.
You can actually see if it works before you spend $1 bazillion and shoot it off.
None of this is original. I mean, JPL has been looking at a Europa subsurface device. There were plans. I don't know if it ever actualized. There were plans to deploy it at Lake Vostok, which is a sealed lake with an ice that you have to penetrate the ice to get to. There are hot smokers terrestrially, and places like Mbari have deployed assets to the hot smokers in order to take samples and assay the ecosystem there. So yes, you could do a lot of this terrestrially before you ever risk something like this.
Looks like you have another question. I don't want to throw it that far.
This is impressive. You just did this in the last hour?
Well, yeah, but I mean,
That was amazing.
This
So,
is known
actually,
stuff
so I'm
we were
getting my
drawing
point.
upon.
Can you be more specific about what the unknown autonomy technologies are to do this? What are the priorities for this mission?
Well, it's untethered
Don't use the
local-
word autonomy either.
Yeah,
And,
untethered localization is, I won't say easy, but it's straightforward how we would develop that for this type of mission. And then you get into harder and harder as you go down the list. So long-term operations without human input, there are oceanographic institutions that send subs under the Arctic sea ice to do mapping and things, and they're in transit for months out of contact with the control, and then they pop back up and start talking. So it's possible, even though we're operating in an environment that's much less known than the terrestrial environment, it's possible to do that level of autonomy. We have indications that that's possible. You get to fault response to recover active, that's tough. That starts to be tough because even with advanced fault detection and management, we're still at some point relying on a human to diagnose what the problem was. And in this case, you won't have that even slow loop with the human to diagnose what the problem was and recover back. So that's a challenge. When you get down to that last item, life detection and analysis, you're really attempting to do a full lab assay with no human input at all, and without knowing what you're looking for before you send it. So
I would offer.
That's the
So
hardest.
I love what you're doing, and I love the mission, I love the vision, I love the challenge. What I would offer, and to respond to this idea for a terrestrial demonstration, this is a great example, Mike, of what some type of centennial challenge, or something where we say we're going to make an award, or one of the awarded challenges of 100K, 10K, or 100K, whatever it is. The first group that goes to the North Pole or wherever it is, somebody's for the ice cap, is able to have a device that goes down, is able to explore and do all this, and within all these timelines. What a great centennial challenge.
Yeah,
So something like that I think is great. And that's kind of what I was getting at.
He gave Lake Bostic as the example, which I think has already been penetrated, right?
I think it has, but I don't know if
Not well.
to this extent, yeah.
Great idea.
Want to use a little power on it?
Mike, do you have a question?
Yeah, a small question. So this kind of triggered the idea that with terrestrial analogs, that humpback whales can actually set up communication across an ocean. You don't know till you get there, but obviously if you could have the autonomy on board to figure out possible communication channels, then you might be able to have something that is less than full autonomy for months and be able to get back to Earth. So maybe
We actually
there's an
talked
autonomy
about,
challenge.
we talked about whale acoustics and
Yeah.
what kind of range you can get with that. So that's definitely something you could consider for this.
Okay, thanks, Butler. This group is clearly ready for this. They had time to come up with a mission name and a logo. And
So that was actually the perfect segue. It's great that we went second.
The more advanced version.
Yes, right. This is the more advanced version. So ENGIAS is the Europa Network Guided Undersurface Intelligent Autonomous Spacecraft. ENGIAS is actually Portuguese for eels, all right? And that is a very, it's a visual concept of what we're talking about here. So we're talking about the mission concept is you have eel-like spacecraft, autonomous spacecraft that can slither their way to a surface vent and get down through the crevasse in a network fashion, very similar. Let's go forward one. Very similar in the idea that as a network of swimmers, if you will, goes down through the crevasses, they drop off a network of breadcrumb relays that can communicate back through the ice and also serve as navigation beacons once the network itself gets down there. And then these swimmers or eels would, in a network fashion, swim around and understand the environment, map out the environment in 3D space using sonar as both a communication device and as a ability to bat-like see in the dark, right, and map out the 3D space, because bats can fly in a cave where there's absolutely no light through all the stalactites and stalagmites and not hit each other. So this network of swimmers would act in the same way in the dark undersurface water. It would have instruments, of course, to detect life, chemical analyzers, organic analyzers, and then swim to the chemical signatures that it's investigating. RTG powered, clearly I think the spacecraft, one of the enabling capabilities is the high volumetric density, energy density power system that can either allow it to have a mechanical means to get through the crevasse or heat to melt its way through the crevasse and to melt its way through impediments in the crevasse. Next one. Oops. So the challenges, obviously we need to be fully autonomous. We won't be able to communicate effectively with the time delay, especially to Earth. The network has to operate together in a network fashion, a cooperative fashion. We need heat or a mechanical means to get through the ice and to navigate the crevasse.
So, and just like Butler, who wanted to select the most challenging mission possible to fully stretch our autonomous capabilities. There are quite a number of challenges that we need to solve through autonomy, navigation, state estimation, where we are in ice and where we are underwater, how to pick promising science location, science goals, how to make decisions under uncertainty, and we believe there will be some uncertainty, and how to establish communications among the network of these spacecraft. And just like what Butler was saying, we need to be able to fail active to recover from faults which will inevitably occur. We need to coordinate and team, so if some of the spacecraft will lose some of their capabilities, how do we redistribute the tasks? How do we coordinate to map out in 3D a particular feature? How do we use some of these more distant spacecraft to transmit their information back to the last breadcrumb to transmission to the surface through, we hope sonar will be able to do that. So lots of challenges and lots of opportunities to really push the state of the art. Any questions?
Any questions? Who's got the box? I think you guys have all just blown everybody away. I wish we had a prize for best summary, but we don't. But there are cookies in the back.
We'll take those.
All right, Ricky, if you could give us the next surprise. We already saw this one.
Ready, you want to try it again?
No, we already did that one too. Who has not gone yet? Did you have a slide? No. Okay. You have a sheet. I'm not sure. Let's see. Does anybody who has not gone yet, do you recognize the file name up here or in one of these two windows here? No? Autonomy 14? Breakout push a little bit up, a little up.
No.
Right there, that one. This one we have not seen. Whose was this one? Okay.
So our group 14 and 15, discussed, it's a bit less polished than the previous two, but we discussed how would we build a habitable Mars base with a team of robots. So the The idea is both to leverage the autonomous car technology as well as this idea of having swarms of robots doing missions. With that, we would be able to build a habitable base on the Mars or on the Moon, or we had also discussed building maybe a telescope on the dark side of the Moon. So to do this, we need a lot of advances in planning, scheduling, tasking, resource utilization, swarming, as well as figure out how to actually build something on the Moon, and tons of advances in the autonomy, robustness to failures, etc. So again, we'd have to learn how to use the in situ resources. We'd have the benefit of lowering the weight and the amount of things we have to send there. The consequence of it's much more difficult than sending things there that we build on Earth, so a bit more risky. The key questions we have left about our mission is why do we do it is a joke, but how do we build the structure with material on Mars? We're not even sure if it's possible. And what do we have to proceed if we have to do it in many different surface conditions? So we discussed on Mars there may be dust and wind and different lighting conditions, etc. And we'd have to be able to perceive things in all those different conditions. Thank you.
I know we have Issa's group and any others. I think there's one more back there. So Issa, why don't you come on up?
So we did not use slides because we want to be different. Actually, the reality is it's the battery in my computer was out. So what we did, we focused on the Europa scenario a little bit, and then we talked about other things, which I'll cover. So imagine the Europa surface mission, the lander, that you can do the entire mission autonomously over the 20-day period. So that would involve the whole autonomous site selection. You're going to have to select multiple sites. You're going to do the autonomous sampling, the sample handling, and you have to do the analysis, and you have to repeat and select different sites based on the information you get. And you can do that autonomously despite the environment, despite the challenges you may encounter, and despite system degradations that you may encounter. And just to let you know that this is not, it may sound maybe too simple, but it's really not. I mean, just think of Phoenix lander and scooping and some of the challenges, despite a lot of the work that went into trying to figure out scooping the sample and depositing it into the sample or the analysis. So that was one technology, which is the whole autonomous, I'm going to call it autonomous sampling for short. The second one was the how do we detect life? So the autonomous detection of life as we know it, and that's a huge area that would really challenge autonomy, and it ties very much into the instrumentation that you would have on the lander. So these would be could be near-term, ambitious, but also probably something that could be envisioned and could be possible within a reasonable time frame. Now, what missions you absolutely have to have autonomy or you cannot do without autonomy? And I think we discussed a number of options, but it became clear that any mission that's going to go to an environment where the environment is dynamic or unknown, or you have to react within a limited duration, that is going to require to have autonomy. So the couple of examples that we tossed around, which is a mission to Titan, and envision you have an orbiter that you deploy an entry vehicle, and then you have to deploy a balloon that has to operate in the Titan atmosphere. You don't have a very good model of you have some notion of it, but you don't have detailed models. It's a very dynamic environment. You can't wait for the next communication cycle. You can make that further more ambitious, and from the balloon you can deploy a submersible to explore the Titan lakes, and now you have three assets: an orbiter, a balloon, and a submersible that they have to interact and communicate. And such a mission, not as ambitious and as exciting as Butler's, but something along those lines was the one that we thought would absolutely require autonomy to be able to operate and interact. So we had a lot of discussion about a specific purpose versus a general purpose type of systems. So one of the key challenges is we talked about if you were going there and you're trying to explore an unknown environment, what would you want to take with you? And you want to take the equivalent of a Swiss knife. You want to have a whole set of tools, and not only just software, but hardware and software tools, because you don't know what to expect and you want to be armed with this. But when reality sets in, you're very limited on mass, power, and all kind of resources. So what you end up with is descoping a lot of these nice things you may have in your Swiss Army knife, and you end up with a realistic mission. And how do you draw the trade between having more flexibility versus, doing what you need to do to meet the constraints? And that's actually one of the key things that challenges autonomy and also challenges more general purpose type of platforms. We also have actually discussed early in the morning and also in the afternoon the whole notion of having some kind of a competition that has an Earth-based field demonstration where you actually do something a little bit different than what's been done maybe before, where you actually deploy the system somewhere in an environment that could be equivalent and leave it. There's nobody there to do the mission, and you're actually fully operating it remotely, and then do challenge that system to do the task that you expect it to do in space, but do it autonomously on Earth. And I think I've been involved in a number of field demos in the past, and I've seen a number of field demos, and there's always a team of people huddling around these assets. And so to do it truly autonomously, you want to do an end-to-end thing. And if you do that to provide a capability beyond what is currently in plans, you can see whether you can, and then you have a bunch of teams competing, then you can see whether there are technologies among these competing teams that are worth further investigation and discussion with the project. I think dream missions, we had a couple of thoughts about dream missions. Some of thought that perhaps a generation of younger folks, kids driving a set of rovers on Mars would be quite engaging, quite exciting, and fairly ambitious. Landing on an exoplanet, it's one of those missions that will be phenomenal if we can get a picture of a landed asset on an exoplanet. These not only require sophisticated levels of autonomy, but a huge amount of advances in propulsion and communication and power and so forth. So with that, I'll wrap it up and I'll take some questions. I want to ask also my team if there's anybody who would like to add or if I missed anything. Okay, thank you. Yes.
In the interest of time, we're going to go to the very last one. I know it's getting very, very late, and we'll just try to wrap this up with this final presentation here, which is Wesley. 1 minute. We got 1 minute till 5:30.
All right, so it shouldn't be more than half an hour here, so. No. All right, so this is going to be a little different. It's really focusing on a technology and then showing a push of a mission that could be implemented with that. As mentioned before, high-performance spaceflight computing is something that is underway with funding from STMD and SMD and Air Force. Just a little bit of a snippet of information on it. Targeting 15 gigops performance. That's not including internal SMD processors in each of the 8 A53 cores, 60 gigabits per second I/O bandwidth, 7 watt depending on memory and I/O utilization, extensibility to allow multiple chiplets to be cascaded, and radiation hard to strategic levels. And that really represents like a couple order magnitude increase above current state of the art. And in addition to the hardware, JPL and Goddard are developing a set of middleware really to serve as a bridge between application software and the complexity of the chiplet and reduce, the cost of entry to developing applications for this. Next slide, please. No, I can do that too. All right, so we briefly looked at a mission concept that really should not be that new to folks in this room. Basically, surface rover performing resource prospecting and mineral mapping with the ability to rapidly traverse lunar or planetary surface and at the same time, do science capture and then switch to high resolution mode for targets of interest. The multi-core architecture of HPSC would enable both simultaneous mobility processing and science acquisition and analysis. You can kind of see one, very simplistic rendering of that here, where you have one of the A53 core clusters dedicated for mobility and the other for science management. It should also be noted that once you do find an area of high interest, you could reconfigure this to pause, the rover to pause, and use the full set of resources for further analysis. And furthermore, the power scalability that's kind of inherent in HPSC, with the ability to turn cores on and off as needs demand, would improve the overall efficiency, energy efficiency of these rovers. Next slide, please. So impact of such a mission would be, the ability to simultaneously traverse and acquire science will allow much larger areas to be covered, really enabling increased return of high-value science data. For future HEO surface missions, this would allow rovers to identify areas of interest for EVAs, to reduce the number of EVAs and increase the science return from the EVAs. And then looking forward beyond that to in situ resource utilization, which is a popular topic at our table. This could ultimately enable URSU, which would, again, reduce cost by limiting mass that needs to be transported to the surface, and then ultimately enabling on-site manufacturing by the URSU gathered resources. Next slide, please. So some of the questions and issues that remain for this is, we're in the process of developing the chiplet, should be ready in roughly 4 years. Ultimately, we need to demonstrate this as a system. There's been discussion of kind of an HPSC ecosystem that not only includes the processor, but things like memory, onboard network, potentially coprocessors, and so forth. And in the sense of coprocessors, we need to investigate what other architectures and devices can be utilized, such as GPUs, and then, as was mentioned here, neuromorphic processors. And with respect to those, are there ways that we can leverage the inherent fault tolerance and radiation hardening of the HPSC to manage other devices that may not be hardened to that extent or hardened at all? The last thing I'll mention is that an issue that's out there is the need to develop application software that leverages the power and flexibility of HPSC. It's really, I think it's safe to say it's going to be somewhat different than things that we've programmed before. Right now we're programming processors that may have 2 cores, like the GR712 or some of the variants of the Space Cube. Expand that to 8 cores or potentially more, and I think the way we need to approach it as application developers will necessarily change. And to that extent, we are developing the middleware to help ease that transition, but it's still going to require some thought for application developers to fully leverage the device for a mission such as this. That, I think, is it. Questions? Yes.
I'll be loud. The question on the memory part of this,
yes,
is that if you don't scale the memory to match the processor thing, the autonomy part of the problem won't be able to be solved. So you need to go up by the same scaling on the memory storage capacity as you do with the processing capability.
Yeah, we are aware of that. That's one of the. There's been investments for a study for memory that's been ongoing. We're hoping to actually start a program to collaborate with other agencies to develop a next generation of memory devices, both in increased capacity, increase bus speed, and also power management, fault tolerance.
With that, thanks very much, Wesley. I want to personally thank each and every one of you for staying so late on a Friday. I know we covered a tremendous amount today. I hope you all learned something. I hope you met somebody new. If you have feedback, thoughts, suggestions about the topics, new mission concepts, ideas for technology, ideas for what NASA should be doing, things that people here from SMD really should hear, please email them to me or to Mike Seablum. Mike, is there any final things that you wanted to say?
I just want to thank everybody, and thanks for coming.
Thank you very, very much. I know it's late, but please have a good weekend. If you're traveling tonight or tomorrow, travel safe. Thanks for coming, and have a good night, everybody.